In this and the next few videos in my linear algebra playlist, I'm going to talk a little bit about higher rank or higher order tensors. And so in this, I'm going to assume that you have maybe a little bit of background in linear algebra, but just for a little bit of background, I guess. So a scalar, which is just a number. So if we have just a number, that is a tensor, but it's a rank 0 tensor. A vector, as we usually understand it, is a rank 1 tensor. And in fact, it's a rank 1 0 tensor, or if it's a covector, then it's a rank 0 1 tensor. And so in the next few videos, I'm going to talk about higher order tensors. So they'd be rank 2 and above. So that'd be things like 2 0 or 1 1 or 0 2. And if you don't understand what I'm talking about here, that's kind of what I'm going to be explaining in the next few videos. And so there are, quite a few people who have done really, really good tensor playlists here on YouTube. I'm thinking of people like eigenchris and Andrew Dotson and this other guy who uh, I'll put him in the description, but it's like X, Y, Z, Y, X, something or other like that. But anyway, like I said, he has a really good playlist on tensors, and I'll put all three of those people I just mentioned in the description below. And there are, of course, other ones. So then the question kind of is, so why should I make one? What am I going to bring to the discussion here? And I've said in other videos that I've done, particularly in the realm of math, that I always like this quote, and I'm probably paraphrasing here, by John von Neumann, who said that nobody understands mathematics, you just get used to it. And so one of the things I'm hoping to bring to the table is just another place where you can sort of get another take on this same subject in order for you to get used to the mathematics. But specifically, what I want to bring to the table is in a lot of tensor playlists, they try to keep things really general, and so they will say like, well, if I have a tensor that looks like this, then I can bring then I can raise the indices or something by multiplying it or by acting on it with some tensor that might look like this. So I have h k. Oh, actually, to raise it, you would want something more like this. And so then you can sort of go T, I, J, and then you can have your G, J, K, and then that will equal T, I, K. And people seem like they're really fascinated by this kind of thing, this whole kind of manipulating indices, and obviously that's important. But to me, it always kind of felt like somebody invented the light switch, and it can turn on the light. But then they want to sit there telling people about the light switch. Oh, you can put it up and you can put it down. And say, okay, but what does it do? What does all that mean? How does it work? And so one of the things I'm going to do is I'm going to sort of show a lot of things very explicitly. So instead of just showing how indices go up and down, I'm actually going to show sort of a lot of the different sort of things actually going on when you're raising or changing indices and things like that. And so that will sort of do two things. So the first one is I think it'll make it clear what's actually happening when you're sort of manipulating these indices, that you're not just sort of changing the position of letters next to another letter, which I think is one of the things that can really be sort of difficult to learn when you're learning about higher order tensors. And so the second thing that that will do is it will sort of bring home the message of why people want to use this shorthand. So, this way of just sort of manipulating indices around with the Einstein summation convention, which is what it's called, where if you have an index in the lower part and an index in the upper part, you sum over them and then you can contract it and things like that, and then you end up with, this T that had an upper index and a lower index here now is a T with two upper indices. And so by actually going through everything in sort of painstaking detail, you will certainly learn why mathematicians and physicists love this Einstein summation convention and sort of a lot of these different shorthands for tensors. So let's get into it. So the first thing is sort of what is a tensor, and this right here is from the Wikipedia page for tensors, and this is showing the stress tensor. And so what you can think of here, so this would be a rank 2 tensor. And so what it's showing is that if we have stress happening, say on this orange surface, you can have stress sort of pushing down or sort of I guess pulling up on it, but you could also have stress sort of in different directions. So these shear stresses, so you can have a stress going over the surface on the actual 2D surface or over this way on the surface. And so one of the things that a tensor does is it can, in this instance anyway, it can tell you sort of what's going on in different directions sort of at a single point. But I think we'll get a little bit more of an intuitive feel for it as we go through these videos, and that this is not sort of the only thing that a tensor can be. And so in order to start making sense of all these different indices and things like that, let's first think about how would we go about building a tensor. And so one thing that I heard early on, I haven't really heard this very often, but one thing that kind of stuck with me is that a rank 2 tensor, so if we have a rank 2 tensor, so say it's Ti or Tij, that's, sort of like, having a rank 1 tensor squared. So squared. So this is an analogy, not the actual definition of a tensor. It's an analogy that a rank 2 tensor is analogous in a way, in sort of a loose way, to like the square of a rank 1 tensor. And so, by the way, I said that's analogous, and that's going to be a little bit common in this playlist too. I'm not going to be as rigorous as some of these other playlists are about what tensors are and how they work. For instance, I'm going to be using the sort of matrix version of it a lot just to sort of illustrate what's actually going on, where, a lot of these other playlists, try to say, well, a tensor isn't always a matrix and a matrix isn't always a tensor and things like that. And, they try to be as general as possible, to be as rigorous as possible. This playlist is going to be a bit less rigorous. I'm going to be focusing a lot more on intuition for tensors and what tensors are. So, as I said, I'm going to be a lot more explicit, which means I'm going to be a lot less general than some of these other playlists are. But like I said, I'm trying to bring something else sort of to the conversation here. And if you want more rigor, then I would definitely check out some of the other playlists that I've mentioned, which, like as I said, will be in the description down below. But anyway, this is kind of an analogy that I sort of liked, that a rank 2 tensor, for instance, is analogous in a loose way to the square of a rank 1 tensor. So we can actually see that when we do what is called the outer product. And so you may have heard of the inner product of two vectors. So if we had our v dot w here, this will give us some scalar value. And so kind of the way that you might have learned it in a really early sort of vector calculus or linear algebra class is you might have seen like v1, v2, v3, and if you dot that with w1, w2, w3, like that, what you end up getting is v1 w1 plus v2 w2 plus v3 w3, and that will give you your scalar. So what you should actually do instead of using these two vectors like this is you would actually use the covector for one of them, and so you'd actually you'd turn this into a row vector, so it would be v1, v2, v3, and it's not just as simple as turning it onto its side, but when you turn something into a covector or the dual vector, but that is sort of the way you would actually show it. And so the inner product would actually be v1, v2, v3 as a row vector, and then w1, w2, w3 as a column vector. But you still end up doing this part right here. There's a little more subtlety, as I said, to a dual vector or covector, but like I said, this is going to be a little bit less rigorous here. But when you do an outer product, you actually do it the opposite way around. You have the column vector and then the row vector, so the order of that matters. And the outer product symbol is this circle times right here. And so what you're doing is essentially just filling in a matrix. And so I've made this table down here for sort of what you do. So you have your W here as your row vector and your V here as your column vector. Then you just sort of take everything and combine it together. So here we take W1 and V1 and put those together. Then we have V1 W2, then V1 W3, and so on and so forth. And so I actually have that right here already. And so this here is our rank 2 vector, or rank 2 tensor rather. And so we could maybe say that that is T, I, J, and the I and J run through each of these subscript letters. So we would have, right here, this would be T11, and then this would be T12, and then this would be T13, and so on and so forth. And so we write it as this Tij like this. And so this is a second rank covariant tensor right here. And so I actually have over here sort of how we designate each of these ranks. So as we see where the IJ is, so here's up top, and that makes it a a contravariant, a second rank contravariant tensor, and then right here is a second rank covariant tensor. So they're both rank 2, but we see that this one has 2 in this contravariant part and then 0 in the covariant part. And we can have mixed tensors here. So T, I in the upper part and then J in the lower part, and that is a 1, 1, but it is still a rank 2 tensor. Then of course we can actually have larger rank tensors, and so here we have 3 indices in the upstairs and then 2 in the downstairs, so it's a 3, 2 tensor, and then is a rank 5 tensor. And so each of these letters, H, I, J, K, or L, and each of these go from, well, I mean, it's kind of a matter of convention. I had it starting from 0 here. Usually when you start at 0, you see them use Greek letters as indices. So that'd be things like, what can make a better mu than that? Mu or nu or sigma, things like that. So usually start at 0. When you have these Latin indices, usually you start at 1, but the idea is that you go to the number of dimensions. And in fact, if you start at 0, you'd actually go to n minus 1 dimensions. And so it's just kind of shifting the number of them over 1. But if we're using these Latin indices, we can probably get rid of the 0, and we'd go from 1, we go 1, and I forgot a 2 here as well, 2, 3, all the way to n, where n is the number of dimensions. And the number of dimensions is actually going to change the size of your matrix, essentially. So I have a couple different examples here. So if we take our outer product of V and W, which you will often see written like this, where the components are outside, and then we have the basis vectors on the inside. Then we can actually use this Tij for our components, and we have this Ei and Ej, which are our basis vectors. And then you can turn that into a matrix that looks like this, where we have T1, 1, and then E1, 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 and then T1, 2, E1, E2, and then T1, 3, E1, E3, so on and so forth. And I put it equal to this because you will often see it written like this, where this these basis vectors like this are left sort of implicit. And so this is a three-dimensional rank 2 tensor. And so 3 means that we have 3 by 3. So it's a 3 by 3 matrix that you would make from a three-dimensional rank 2 tensor. Then we can see down here, so I changed a few different things. So now I have it as a mixed tensor, where I have the mu in the lower index here and the nu in the upper index here. So we get this T mu nu like this. We can have the basis vectors explicit like that, or you can have it implicit like that. And we see here that this is still a rank 2 tensor. That's why we have 2 indices here. But now it's 4 dimensions. Our mu and our nu run from 0 to 3 rather than 1 to 3. And so that gives us 4 dimensions. And so that makes it a 4-dimensional, though still rank 2 tensor. And we can see that this is a 1, 1 tensor, where the first one is the contravariant, and the other one is the covariant indices. So remember from up here, contravariant and covariant. And so the lower indice here is the covariant one, and the upper indice here is the contravariant one. And you'll see that on the t here and in the implicit one, I have it so that the mu shows up to the left of the nu. So one is lower and one's upper, but the mu shows up left of the nu. And so the order of those things matter because it has to do with these basis vectors here. Or these basis vectors, which we are combining them with this right here, which is the outer product or the tensor product. And that becomes important later too, because each of these basis vectors here are treated differently, and we will find out how that works later on. So this here, this right here, I liked this image because it showed kind of how a matrix would be generated for different ranks. So the rank 0 is the scalar. Rank 1 is a vector, so the vector as we usually understand it. So this shows it as a row, even though if you've taken any linear algebra, you're probably used to seeing vectors as column vectors like this, and that can go on to Vn. And so the n is the dimension, but it's rank 1, and that's why it's just this single column. Then we can have a rank 2 here. And so this is a little bit misleading. There should be another row of boxes here because it should be a square matrix if it's a tensor. So it should be 4 by 4, which means that it's a four-dimensional rank 2 tensor. Then rank 3. So once again, this is a little misleading. We can probably forget about this part right here and just look at this. And so a rank 3, which would have 3 indices, so that'd be something like T, H, I, J, like that. And so we'd have, right here, T1, 1, 1, and so on, going through here. And so that's actually what I have over here. And so you can see that like this would be sort of that first layer in the front on this one over here. Then this would be that second layer sort of in the middle right here. Then this would be that back layer back here. And we can see that the indices, that the third index is the same in all of these ones. So it's 1 in the front, and then 2 when it's in the back, then 3, or 2 when it's in the middle, then 3 when it is in the back here. And so with all of them at 1, we run through everything like we would in the rank 2 tensors. So the 1, 1, 1, 2, 1, 3, then going down the 1, 1, 2, 1, 3, 1, so on and so forth. Then we do the same thing again. So I said that it's the analogy is kind of like a rank 2 tensor is sort of like the square of a rank 1 tensor, which we kind of saw. So if we have, say, V, 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 or this is actually the outer product, V, V, which we can say is sort of like V squared in a way, because we were taking our V1, V2, V3 as our row vector, and then our, well, actually, with the outer product, we were doing it the other way, remember? So V1, V2, V3, then multiplying it by V, but as a row vector like this. And so a rank 3 would be like if we then took another one. So it'd be kind of like having V cubed. Once again, this is just an analogy. This is not how it it actually works. This is the sort of non-rigorous analogy, but it'd be kind of like having v, v, and then another v like that. So taking the outer product of three v's. And so you do the outer product of this, and you'd end up with your, sort of rank 2 tensor here, and then you're doing the outer product again with v, and that will give you your rank 3 tensor here. This should be an ij. And so, like I said, it's kind of the analogy. And so there can be higher rank ones. You would need more than 3 dimensions to show sort of the matrix version of that. And that's why, when you're trying to be more rigorous, you say that a lot of the more rigorous playlists will steer away from this sort of matrix representation because, I mean, for one thing, even with just this rank 3 matrix, it's like, how does that work as a matrix and sort of the way that we understand from our sort of, linear algebra where we have, some matrix acting on our vector becoming, some other vector. But if you have, like a rank 3 tensor like that, then you are sort of acting on a vector. What does that even mean? How would you actually carry out that sort of operation? But anyway, this, like I said, was sort of the introduction here. The thing that I really wanted to get through here was this sort of outer product and how we can actually build higher rank tensors from these lower rank, rank 1 tensors. And, like I said, you can continue on. You can actually, you can build even higher rank tensors by, combining more than 2 rank 1 tensors. And so yeah, that is kind of the main takeaway from this video. In the next few videos, I'm going to be talking about some of the tensors actually that you find in the Einstein field equations. So that's things like the metric tensor, the Ricci curvature tensor, which is a contraction, which I'll talk about, of the Riemann curvature tensor, and the stress energy tensor, which is a little bit different. Well, it's a bit different than this just stress tensor. But anyway, we'll get there when we get there. Like I said, the main thing I want you to take away from this one is just sort of how we build a tensor, a higher rank tensor from lower rank tensors, and then sort of what this idea of rank is. Yeah, so anyway, in the next video, as I said, I will go through a little bit of stuff with the metric tensor and sort of get more of an intuitive understanding of what the metric tensor is and how it works and things like that. So anyway, I hope you found this video helpful in your journey to understand what tensors are, and I will see you in the next video.